Welcome to This Explainer. Today, we're going to demystify solid-state physics and really dig into the invisible, absolutely fascinating quantum mechanics that dictate exactly why and how a material conducts electricity. Seriously, once we break down the microscopic rules of the game here, you're never going to look at everyday electronics the same way again.
Okay, before we get into the heavy mechanics, let's start with a foundational mystery. We see it literally every single day, but we rarely stop to actually think about it. Why do certain materials act as perfect conductors, just happily ushering electricity along, while others act like impenetrable barricades? I mean, how can the exact same electrons flow totally freely through a copper wire, but get stopped dead in their tracks by a piece of plastic or rubber? To answer that, we're going to tackle this from the quantum level up. Here's our agenda for today. First, the conduction mystery. Second, valence and conduction bands. Third, the almighty band gap. Fourth, conductors, insulators, and semiconductors. And finally, manipulating semiconductor materials. All right, let's jump right in with Section 1, the conduction mystery, the flow of electrons. You know, electrical conduction can sometimes feel like magic, but it's really just a massive microscopic chain reaction. Specifically, a long chain of momentum transfer. Think of it like a super crowded room where one charged particle bumps into its neighbor, and that neighbor nudges the next one, creating the steady flow of current. The electrons themselves don't actually have to sprint all the way from a power plant to your living room. They just need enough mobility to pass that momentum down the line. And this brings us right back to that everyday observation. It is so wild that a standard power cable uses metal, like copper, which has this delocalized sea of highly mobile electrons, to facilitate that endless nudging, while the rubber wrapped right around it completely shuts the whole process down. But what is actually happening inside the atoms of that rubber to trap those electrons so perfectly? Well, to figure that out, we have to zoom way in and look at the quantum states where these electrons actually live. Which leads us to Section 2, valence and conduction bands, the quantum traffic jam. Inside any solid, electron energies are grouped together into what we call bands. Picture the valence band as a totally jammed parking lot. At absolute zero temperature, this is where all the electrons are hanging out. They are tightly bound to their atoms, just stuck in place, nowhere to move. But on the flip side, the conduction band is like a wide-open multi-lane highway. It's this higher range of vacant states. And when electrons manage to get up into this conduction band, they're completely free to accelerate and carry electric current. So the big question is, how does an electron get out of that jammed parking lot and onto the open highway? That brings us to Section 3, the almighty band gap, the bouncer at the club. So between that valence band parking lot and the conduction band highway, there is often a forbidden zone. We call this the band gap. It's an energy range where absolutely no electronic states can exist, dictated purely by quantum mechanics. It acts exactly like a toll booth or a really strict bouncer at a club. To get an electron across this gap, you have to pay a very specific minimum amount of energy, usually in the form of heat or light. If you don't have enough energy, nope, the electron stays stuck in the valence band and absolutely no current flows. To really put this into perspective, let's look at some actual measurable values for these band gaps, which physicists measure in electron volts. It paints such a clear picture. Silicon, for instance, requires a pretty moderate 1.14 electron volts for an electron to make the jump. But then look at diamond. It demands a massive 5.5 electron volts. And silicon dioxide, which makes up a lot of common glass and sand, requires a staggering 9 electron volts. This one simple number completely dictates how a material behaves out in the real world. Now, when an electron finally does pull off this jump, it goes through a really specific sequence. First, it absorbs some external energy, maybe a photon of light or a tiny quantum of vibrational heat energy called a phonon. Once it gains enough energy to cover the cost of the gap, it jumps. Though, side note, in some specific materials, it also needs a quick shift in momentum to make it across. Finally, it arrives in the conduction band, ready to flow. But here's the coolest part. It leaves behind an empty space in the valence band, known as an electron hole. And that hole essentially acts like a positive charge carrier all on its own. All right, moving on to Section 4, conductors, insulators, and semiconductors. The big three. So, taking what we just learned, it really all boils down to the size of that gap. Conductors, like our copper wire, have overlapping valence and conduction bands. There's literally zero energy gap, so electrons just flow freely without needing any extra push.
Semiconductors, like silicon, sit right in the middle with an intermediate gap of about 1 electron volt. At absolute zero, they're basically insulators, but at room temperature, there's just enough ambient thermal energy to pop some electrons across the gap. And then we have insulators, like rubber or glass. They have a massive gap, usually over 4 electron volts. Their electrons are locked down tight, and normally current is totally blocked. But this dynamic creates a super counterintuitive contrast when you introduce heat into the equation. If you heat up a metal conductor, its electrical resistance actually goes up. Why? Because the heat makes the atoms in the crystal lattice vibrate crazily, creating those phonons we talked about. These vibrations act like the bumpers in a pinball machine, constantly scattering the already free-flowing electrons and slowing everything down. But if you heat up a semiconductor, its conductivity goes up. That same thermal energy is giving more and more of those trapped electrons the exact kicks they need to clear the band gap and join the conduction highway.
However, here is a little secret for you. A perfect insulator doesn't actually exist. If you apply an extreme, massive electric field to an insulator, you'll eventually hit its breakdown voltage. The electric field becomes so intensely strong that it literally rips the electrons right out of their tightly bound atoms, kicking off this rapid chain reaction. The material just suddenly floods with mobile charge carriers and conducts a massive surge of current. This phenomenon, called electrical breakdown, is exactly what's happening when a lightning bolt suddenly turns the insulating air in the sky into a superheated, highly conductive plasma. Okay, so understanding all this foundational physics is cool and all, but intentionally manipulating it, that's what built the modern world. Which brings us to our final part, Section 5, Manipulating Semiconductor Materials, Engineering the Gap. We definitely don't just settle for taking semiconductors as nature provides them. Thanks to a brilliant engineering process called doping, scientists can intentionally introduce highly specific foreign atoms or impurities into a semiconductor's crystal lattice, and by carefully picking and choosing these impurities, we can drastically alter the material's charge carrier concentration, totally fine-tuning its conductivity and bandgap energy. For example, we can create an N-type semiconductor by adding elements like phosphorus or arsenic to silicon. These atoms naturally have extra valence electrons, so they pack the material with negative charge carriers. On the flip side, we can create a P-type semiconductor by adding elements like boron or gallium. These guys have fewer valence electrons, which introduces a bunch of extra electron holes, or positive charge carriers. And when you literally snap these N-type and P-type materials together, you get devices that can control the flow of current with absolute microscopic precision. I mean, this precise bandgap engineering is the absolute bedrock of the tech you use every single day. Take LEDs and laser diodes. When an electron falls back across the bandgap into the valence band, it releases a photon, and the exact physical size of that bandgap that perfectly dictates the color of the light it emits, from deep infrared all the way up to violet. Or think about solar cells. Scientists painstakingly engineered the bandgap to capture sunlight as efficiently as possible, a balancing act governed by a fundamental physics rule called the Shockley-Queisser limit. If the gap is too high, the photons just pass right on through. If it's too low, all that excess energy just gets wasted as heat. And of course, the transistors in your computer or smartphone use these meticulously doped junctions as tiny microscopic switches, controlling current flow to process all your digital information. So we've got all the way from the basic mystery of a copper wire versus a rubber coating, right down to the incredibly precise engineering of smartphone transistors. And it is all governed by the mighty band gap. But as we look to the future, things are getting even wilder. Take crystals known as quantum dots, for example. Thanks to the quantum confinement effect, just shrinking the physical size of the dot actually shifts the energy states and widens the band gap. So I want to leave you with this provocative thought. As we continue to shrink our devices down to the atomic level and exploit these incredible quantum behaviors, just how far can we push band gap engineering before we finally hit the absolute fundamental quantum limits of physical materials? It's a massive question, one that is driving the next generation of physics, and I really hope this explainer has given you the foundational lens to understand it when it happens. Thanks for tuning in.